Hi, today I'm going to walk you through chapter 7, which is about the Riesz representation theorem or duality theory for continuous functions, if you wish. So we've gone through this whole book, integrating all sorts of functions, mostly L1, but also this LP spaces and L infinity, without even talking hardly at all about continuous function. I mean, in chapter 3, there is something about continuous functions being dense in LP under certain conditions. But beyond that, nothing. All right, well, maybe because there's not too much to say. Yeah? There's also the theorem in chapter 2 that if you have a continuous function, then it's Riemann integral and Lebesgue integral coincide, or you can allow some discontinuities to account of Riemann. Or a set of measures 0. But yeah, so I mean, integrating continuous functions, I mean, they're just in there, they're in the LP or L1 theory, but the duality theory gets actually quite messy, I would say more complicated than the one we have for, LP, the dual is LQ. So what is duality theory again? You have a space, vector space, like the set of continuous functions, or if you're on Rn, set of continuous functions that go to 0 as the variable goes to infinity. Okay, so that's even a Banach space, and then you can ask, what are my continuous linear functionals on this space, or how can I characterize those? And then the answer is integration against the measure. So we know that the set of measures is a Banach space, but that in itself has never been used to realize the dual of something. So I mean, when we talk of L1, we always have a fixed measure mu, right? And then L infinity mu is the dual. But here, we just have continuous function. There is no a priori measure. We're talking about continuous is continuous. We have to connect that to topology. Just nothing to do with sigma algebras in the other. And then it turns out that the set of all, or the Banach space of all either signed or complex measures, depending on to work in the complex or the real world, becomes the dual in the sense that each linear functional, you have a linear functional t, and then you want to apply it to some continuous function f on some space that we will specify shortly. Then you can always find, given t, you can find a measure mu such that this integral becomes realized like this. That's all there is to this chapter, I would say, more or less. Well, in broad terms. Getting to this statement is however, wading through a swamp with mosquitoes and anacondas. So, as I have mentioned earlier, I will not be as I will not focus so much on the details any longer. Rather, I will try to lift out the key ideas of what's going on here in these 3 sections, so that you, when you read it, can easier orient yourself. Because I mean, this book is like just stashing results, right, and not always explaining very well what's going on. Also, in this chapter, they do everything in a very abstract setting, which sometimes makes the proof more abstract and certainly less intuitive. So I will do the intuition, right? So I will provide you with alternative arguments that work in Rn, which is a setting where we can relate to. And then hopefully when you read the theorems, like, yeah, okay, he's trying to do that, which I know what it is. He's just doing it in a more general setting, and that's why the argument is complicated. But in reality, it's not that strange, the statement he's after. That's what I'm aiming for. That's what I want to achieve. Whether I achieve it, well, you be the judge. Let's get started. All right, so I will work in RD. More generally, it's locally compact Hausdorff spaces or something, but I work here in this lecture in RD. We'll occasionally mention the more general setting. Riesz, by the way, there were two of them, Marcel and I don't know, Fabiano. That wasn't his name, but doesn't matter. There were two of them, they were Hungarians, but one of them was actually active in Lund. And I don't know if this is that Riesz or it's the other Riesz who gave his name to, but they were both mathematicians. So, and then there are a lot of theories they got themselves. So yeah. So let K of RD be the set of continuous functions, of course, then on RD with compact support. Now, if you have a function in usually in this LP space theory, the support, you have to be careful when you define it because we have this, most of the time a function is not defined up to sets of negligibles. I mean, the natural definition of support is to say, all the points x such that f of x is not equal to 0. And that definition is problematic for L1, for example, because given one representative of an equivalence class, this set will not be the same as if you take another representative, right? But for continuous functions, we don't have this problem. A continuous function is given by the function. There's no equivalence class or whatever. If you have a different continuous functions, then they will differ on a set of positive measure, whatever measure you have. So, but not for every measure. But anyways, right. So this is the definition of the support of a continuous function, and we want that. No. Okay. So if you think of something like this, all right. Okay, so it goes to 0 here. Then actually the point where he reaches 0, that is 0, right? So this becomes an open interval. So we want the support to be a closed set. So we do the closure of this set. So we just include all boundary points of this set, and that's what we're going to call the support. All right. So continuous functions with compact support, it just means that inside some big ball is where all the action happens. So outside of that big ball, the guy is 0. That's the only, because closure comes, that set is closed, it comes from us taking the closure, right? So compact support just means that support is actually bounded, at least in RD. Okay, and then so there are a few versions of the Riesz representation theorem. So let me give you the first version. Right, so the first version says that if I is a positive, I always mix up positive and non-negative. This, of course, is allowed to take value 0 as well. Okay, linear functional on this vector space, it's even a normed vector space, but we don't use that, we just use positivity. So as for now, we just have the vector space. Plus minus. There exists a unique Borel measure mu such that I of f is equal to the integral f to mu. So let's call this fellow I here as well. So we're consistent. Moreover, then we want to characterize what properties do these measures have when mu of k should be finite. for every k compact. So this is not necessarily a sigma finite measure. And vice versa, if you have a measure k, it's not written here, but it's kind of immediate, right? If you have a measure k with this property, then since these guys have compact support, it means you will always get a finite number in this integral formula here, right? Because this integral is less than the measure of the support times the supremum norm of the maximum of the modulus of f, right? So, or no, yeah, yes. Okay, so here we don't use continuity or anything else. Instead, we use this positivity. Important. So examples. In R, for example, f becomes mapped to I1 of f is equal to integral f the lambda. That's one guy, and another guy would be integral f, and then take Dirac measure at 0, which just becomes evaluation at 0. Of course, we can evaluate at any point. All right, I don't have more exciting statements lined up, but note that this guy is bounded. If we now add a norm to this space, which norm do we have? Well, the maximum value of the modulus, supremum norm, if you wish, is the natural norm, right? So I'm going to denote it with 2 lines and an infinity sign, just like before. You know, essential supremum, if you have functions that like L infinity functions, right? But here we don't have that problem, as I already spoke about. So right, the essential supremum here is just the maximum value of the continuous function. Okay, so if now we add this norm here, then we have a norm space. It's not a Banach space yet. Well, it's not, period. But anyways, you can have linear functionals on norm vector spaces, whether or not they are Banach, and ask whether they are bounded or not, or continuous or not. It's the same thing, right? We did that exercise. That was in chapter 3.2. These are equivalent for linear functionals. Okay, so this one is bounded because clearly the value at 0 is less than or equal to the maximum value of the modulus. Here we do not have that. And how do we see that? So just think of functions that look like this. So here you have n, here you have n plus 1. We can go down linearly or whatever, we don't care. Minus n plus 1, and here you have minus n, right? So it's 1 and then goes down. If I integrate here, let's say we have straight lines here, yeah, just to get good numbers. Then the integral here is 2n plus a half here plus a half there. So if we call these functions fn, then you have I1 of fn is equal to 2n plus 1. But of course, each fn has norm 1. So you have a sequence of functions that remain bounded, but the value of your functional goes to infinity, then you have an unbounded linear functional. So this brings us to the second version. So anytime you want to involve signs or complex numbers, you know, cancellation is always a problem in mathematics. So then you have to be more restrictive. You know, we have seen this many times in the course. So it's just this phenomenon again. So now, if we remove positivity and replace it by continuity of the linear functional, then we get finite measures. Yeah, which is clear. So here, this example shows that lambda can be an infinite measure in the sense that the full space has infinite measure. And if you have a positive, if you now assign measure, the positive part takes infinity and the negative part takes infinity, then that's bad. We don't want that in the Hahn decomposition. We don't, want to deal with plus infinity minus infinity because that's not a well-defined number. So this is very natural, actually. So version 2. Right. So if I is a continuous linear function on this space, there exists a unique measure mu, and now I use this notation here, which was the Banach space of all finite sign measures. And then we have that, okay, this formula we knew, but there is an additional twist to it that the norm of I as a bounded linear functional, this supremum I applied to f divided by f for all f's, this norm as a functional is equal to the norm of mu in this space, which is precisely what we want, right? If we talk about duality, you don't want only that every functional can be represented by something in your space that you want to use to characterize, but you want also that this identification is isometric. Yeah, so bijective and isometric, norm here, norm there, it's the same. Then mathematically, there's absolutely no difference. It's just like I'm called Marcus in Swedish and Hassan in Middle East, but it's still just me. So, right, a remark which I won't write down, but if this is a continuous linear functional with values, you can also throw in here complex values. As a function from Rd with values in the complex plane, then nothing here gets very more complicated. You just replace it now with complex valued measures, and then the theory is again true. So that would be version 2.5 maybe. But there is a version 3 here, and so there is some sort of imperfection here. Both these is that, so the dual is a Banach space, but the space we work with is not a Banach space. It's just a norm vector space. But it's very easy. So there's something, actually, this is an abstract construction in functional analysis. If you have a space which is a vector space which is norm, but it's not complete. Yeah, so you're just short of being a Banach space with the completeness. Then you can take something called a completion. So yeah, you can embed it in some abstract space. And actually, it's a stupid construction. You just, you want all Cauchy sequences to converge in a complete Banach space. So then the completion is actually a space which consists of all possible Cauchy sequences, and then if they converge to something that exists in your original space, you identify them, and if they're converging outside, then that's a new point somehow. It's very just mathematical nonsense. But here in this concrete setting, the completion has a very concrete representation. So we don't need to deal with any of that. The completion here is just all functions that are continuous and that decay to 0 as x goes to infinity. So let C0 Rd be all continuous functions such that limit as x goes to infinity, f of x goes to 0. Of course, how do we interpret this? We mean, of course, So the limit as r goes to infinity, and then you do a supremum modulus x bigger than r, and then you look at modulus f of x. Right, that's how to interpret this, right? So it uniformly becomes small if you're far away from the origin. So this is a concrete space. Now, if you have a function, let's do on the real line. So you have a function like this. So a typical example could be the Gaussian e to the minus x squared. It goes to 0, but then very fast, but it never reaches 0. But then, of course, if you want to approximate this with continuous functions with compact support, we can just let it go down to here n and minus n by, let's say, a diagonal line slope -1 and 1, right? And then we can call that, so if this is our f, then the function that goes down like this, let me call it, okay, I use a different font color. This is my fn. And then, of course, because we have this, so in the supremum norm, the difference between what we have here and the difference between these two functions goes to 0. Maybe in RD, you can't really just replace with the line, so one has to be a bit more. In RD, what you do is you work with something called approximations of the identity. So what you would do is you just chop off your guy here, and then you do a convolution with something which has a very thin support and positive and integral 1. And we discussed this earlier in the course. Then you get some sort of, at each point when you convolve, you get some an approximation of the value here. So if you convolve these two, you get something which is 0 outside near where you chopped off. So if you add, this one also has some extent that you have to take into account, but it's just like here, it will go down where you chopped it off to 0, and then inside it will be very close. So that's a way of approximating in RD any given function f here with functions of compact support. So of course, here I just painted 1, this is my phi n, but so in this process, the approximation of identity is always a sequence of functions, right? That support gets smaller and smaller and smaller, and the height higher and higher, and the integral is always 1, right? Anyways, so like that, we see that K
is dense in this space.
And just chipping in here some additional information as I post in post-production. So the corresponding statement in the more abstract setting of locally compact Hausdorff spaces, then we cannot do convolutions either. And I will explain that in more detail very soon, but just to say now that the corresponding statement here that I just proved in that setting, then you need something which is called Eurysohns lemma, which is a key result in topology and also one of the main results that they just state without proof that you need to use in section 7.1. Back to the argument.
Yeah, and it's an exercise in functional analysis that if something, well, it's almost immediate. So if something gives a bounded linear functional here, since we have the same norm over here and every element here can be approximated arbitrarily well here, that will be a bounded linear functional here as well with the same norm. So if we have a characterization of the bounded linear functionals of this, we have a characterization of the bounded linear functionals of this, and it's the same thing. So version 3, which is the most beautiful version, the dual of C0 is M. And then yeah, RD or whatever. So, as I said, the book works in more abstract generalities. You can add stuff here, but the measure space is the dual of these sets. Either complex or sign. So an outline of proof here. Yeah. The hard part is to prove this, the version 1, right? If we have that, then it's not clear really how, but we need something like the Hahn decomposition then for bounded linear functional, so we can somehow write a given linear functional that's bounded as the difference between two non-negative ones. And how we do that,
I will explain in the next lecture. I decided now I split this up into 2 lectures. So today we're mainly going to go through 7.1 and 7.2 up until these key theorems start. So more or less up until 7.2.8, which is the first version of the Riesz representation theorem. But already it's a very good exercise. It's not that complicated to single out the positive and negative part of a bounded linear functional. So it's a good exercise to actually try to work it out yourself. How would you do to achieve that?
once you have that splitting, then you just do version 1 to the positive part and the negative part separately and add things up, right? So then from this you get a measure mu, which is finite because of the boundedness. That gives you the half of your linear operator, and then you get a finite measure from the negative guy, and you just add them together, and yeah, and then you have to check the norms, whatever. But that's, I'm not saying it's easy. I'm just saying that follows lines that we have already seen before in this book. However, here to get to this statement, we will need to cover new ground. I mean, mentally. So that's what I will focus this class on. Okay, so a bit about this extension or the general setting. So this statement here is true not only for RD. All right, so let me add that now. But we also have, for example, C0 star of the natural numbers.
Is equal to
Finite measures. And what is this? I mean, this is all sequences. n goes from 1 to infinity, such that the limit is 0. What does this become? Well, a measure on n, it just gives a value to every point, right? So it's just a new sequence. If it is a finite measure, actually, then we know that if we sum up. All right, so this guy comes from here, but then the guy here will also be a sequence. It's called Bn and go from 1 to infinity. And then since here we have finite sign or complex, we know, so the norm of this as a measure, well, that's just, this is like the variation of this measure will be nothing but this, right? And that is actually equal to the L1 norm of the sequence. Let's put here M. So we see that the space of sequences that has a limit 0, as n goes to infinity, is actually all finite sequences, sorry, all sequences in L1. So yeah, this space, actually C0n is often called little c0. So then we have a little c0 dual is equal to L1. But this is really special for the natural numbers. Usually these measure spaces, of course, is much more complicated. I mean, this is, yeah, so we know the Raven-Accordion theorem, or the Lebesgue decomposition theorem says that if I have a measure on a general space, there's an absolute continuous part, which is actually somehow, so underlying here, you can think of, you have the counting measure, and then L1 of the counting measure, that's the absolutely continuous part of a given measure, and then there's often a singular part also, but in this simple setting with the natural numbers and counting measure, there is no such thing as singularity, so then that piece falls out. Okay, but it gets tedious to start to write this theorem over and over again in new settings every time, which is one of the reasons why then they strive for some more abstract version of this statement. The other reason is, of course, it generates beautiful mathematics, and that's, a bored mathematician, he has nothing to do, he will start to just abstractify something to get a unified theory. This is like like a horse grazing grass or something. It's just like what it does automatically. So the most general setting where we can prove such a result here turns out to be, we have to replace RD with locally compact Hausdorff spaces. Now this sounds completely new. Why don't we just work like before with some abstract space X and have some sigma algebra A? No, because here the foundation, the basis here is continuity. Continuity is based on topology. It has nothing to do with measurability. But to have measures, we need sigma algebras, right? But first, okay, well, I'll get to that later. But so what we will start with, we will continue, consider K of X, where now X, comma T, or whatever, is a topological space. All right? And then we also have C0, once that, all right, so the topological space has compact sets, so then you can define functions with compact support, but then, all right, so what's the corresponding of this limit process, or this here, that's to say that something goes to 0 when it goes to infinity, it would be to say that, okay, given epsilon, I can always find a compact set such that outside of that set, my function is less than the given epsilon, right? And then I define this space, right? This would be the set of functions f from x into R complex, such that for epsilon, there exists compact set k, I don't even write that down, such that f of x is less than epsilon for all x outside of the compact set. Okay, and now with this, we have a more general version here is C0 star x equals m of x, but then you go, but we need a sigma algebra here at least. Now we need the sigma algebra. Yes, but anytime you have a topology, you have something to start working with, right? So just like the Borel sigma algebra is generated by the open sets in Rn, Rd, or yeah. So if you have some abstract space X, you can take that as a collection of sets that generates, by proposition, 1.1 something. There's a smallest sigma algebra that contains those open sets, and we're going to call that the Borel sigma algebra on X. So that leads us to this new concept, B of X. This is the Borel sigma algebra. And now, M of X is all finite measures, finite signed or complex, with respect to this sigma algebra here. Okay, so here's a fact for you. If you haven't taken topology yet, there are many stupid topologies. Topology is a hocus pocus idea somehow. I mean, it's so general that almost anything could be a topology, right? What does it say? The topology is a collection of subsets of a given set, X, such that we're allowed to take uncountable unions, and the empty set should be in there, and maybe the full space also.
And finite intersections.
That's it. So you can make up all sorts of stupid things that qualify as topology. So we need to exclude the most extreme ones. And then if you take a course in topology, it's rather boring. There is some sort of hierarchy there. You add assumptions on your topology and it gets closer and closer to something useful. So here this statement is true when X is a locally compact Hausdorff space. What means locally compact? I have to look it up. But Hausdorff, at least, just to show you, like, you could even have topology such that every open set contains, you know, if it contains this point, it also contains this one also. You can have different open sets, but they always, you can never separate these 2 points. What sort of a stupid topology is that? So Hausdorff just says that if I have 2 points in my space, I can do a circle here and a circle there, and these are open. Yes, I can separate 2 points with 2 open sets. That's the Hausdorff condition, and then locally compact. I hope it's written here on my paper. All right, so the way that mathematics evolves, and also the way it's being done, and the way to learn it, is to go from the simple to the more general, right? So if I were to prove this theorem, let's say, you know, it wasn't proved already, I'm Marcel Riesz, the way I would approach it is, okay, how do I prove this on the real line? Step 1. Step 2, all right, how do I do it now in several variables? And once I'm done with that, I would be like, okay, which tools did I actually use here? What do I need from an abstract topological space in order to pull through exactly the same argument with the same ideas, right? And then I would invent names for whatever topological requirements I needed in order to have those things, right? So that's how this statement has evolved, and that's, I'm sure, if you look at the history of it, and that's also how you have to understand it. So it's better to first learn the proof in RM, and then you go like, okay, now that I understand the key ideas, I you know, you can kind of like feel it that yeah, this has been done. Greater generality. By the way, I forgot to mention what is locally compact. It's just that if you have a point, okay, so there are huge open sets around it, right? But you want it to locally look like a compact set in a neighborhood. And so it's not enough to say that the point itself is always compact. The 1 point set is compact. But so there should exist some open set U in your topology, such that you can take a K compact around it, and then you call that locally compact space. And then Hausdorff separate 2 points. These are the 2 things it turns out we need in order to be able to do whatever we need to do in RM, or need to pull through this theory. Now, what are these 2 key ingredients that we need for the proof? I will discuss them first, show them to you, and then we discuss a bit how, yeah. All right. First, we'll discuss the ingredients, then how to lift it to locally compact Hausdorff spaces, and then a bit about how to do the main proof. Right, so functions separating closed sets and partitions of unity, especially the latter, is something used frequently in mathematical proofs all over the place. So let's first look at what this means. So there's a proposition here. Right, so given 2 closed disjoint sets, E and F in RD, there exists a function f here. So C of RD is just continuous, no other restriction than just continuity. 0 less than f means as a function, right? So for all function values x, for all variable values x, f of x is less than 0. Sorry, bigger than or equal to 0, less than or equal to 1. All right, and what does this function do? It's identically equal to 0 on the set E. So we have some guy E here, we have f here, the function is 0 here, and then it's identically 1 over there, and in between, we don't care. Yeah, on the real line, here's my E, here's my f. All I need to do is to have a function which is 0 here and goes up and it's constantly 1 here, and outside it can do what it wants.
Well, with the restriction, of course, that has to stay between 0 and 1, as just stated. So I got a bit carried away there while painting.
So this is, just think about it. It's intuitively obvious. That's actually non-trivial, even in RD. You have to do some sort of construction because sets, at the end of the day, closed sets can be very complicated. Yeah, like counter set, for example. Right. And if we're in a locally compact Hausdorff space, the fact that you can do this is called Urysohns lemma, and it's one of the key results of this stupid topology course. I'm not sure if the H goes here or maybe somewhere else, but I'll Google to be on the safe side. God damn it, people, annoying. Okay, so the Eurozone lemma is there's probably some German guy here because this is Sohn. And it actually says that in a normal topological space, you can do this. So then you need a separate result saying that if you have a locally compact topological space, probably Hausdorff also, then that space is normal. Normal is another word that's just so overly used in mathematics that there's so many things that, normal, it's an adjective, right? It's used to describe something as not out of the ordinary. But it seems like in mathematics, just you need to call something, you have invented a new property and you call it normal. Nobody else claimed it in that field. That's the first thing you comes to mind. It's very strange, but or not helping really. But anyways, that's the terminology. But anyways, this is true in the locally compact Hausdorff spaces we're working in, so that's good enough. All right, so how can we construct such a function in the RD setting? I'll just do an example, and actually the example will guide us to the proof. So let's do. Here's the x-axis, is the y-axis, we are working RD. And then my E is going to be all the points y bigger than or equal to 1 over x, right? So the set of points x, y such that inequality holds. It's not here. That's a closed set. And then the other closed set is going to be this all points where the y coordinate is negative. Okay, so everything below the x-axis on it. So now locally compact Hausdorff spaces are not necessarily metrized. There's no metric there, at least not in the beginning. There is some like condition that allows you to construct a metric that gives back your topology. I forgot which topologies that holds for. Doesn't matter.
Actually, it turns out that it does matter. At least they devote some attention to this at the end of 7.1. So then I might as well just explain it. So it turns out that a space is metrizable. So the open sets are given by a metric. I won't explain it. You just Google it. So metric gives distance between points, and then open sets are like all points with which. So then you can define the ball, center x, and radius r as the set of all y, such that the distance from x to y is less than or equal to r. And this distance, if you have a normed space, you just do the norm of x minus y, but the metric is more general. Right, so if a topology is generated by a metric, the argument we'll see coming up now in the main lecture, then it becomes much simpler to work, because then you can use this metric and our intuition works much better. So then you want to know which topological spaces are generated by a metric. So if these open balls, you can take them as a basis for your topology. So you just do unions of open balls and you get all open sets. Now it turns out that a space is metrizable if and only if it has a countable set. That don't need to be balls, but a countable set of open sets that forms a basis for its topology. Okay, so this is true, for example, in RD. So in RD, of course, you just take balls with any center and any radius r, but that's uncountable. But then you can restrict attention to x, which are rational coordinates, and then you restrict attention to rational radii, and it turns out that these are enough to generate your topology, and this is then a countable set of balls, right? So our usual topology in RD has a countable topology. So yeah, you have some topology, it has a countable basis, then it's metrizable, meaning you can use the topology to construct some sort of function d that gives you back, there is a metric and gives you back your topology. Okay, so there are some statements in the book which are, so then this comes back in few statements like if there's a countable basis, yeah, all right, but still most results, they go to great lengths to deviate or to get around this assumption, because the Riesz representation theorem actually doesn't need that, right? So even maybe most topologies you will ever encounter do have this property. Mathematics we want to generalize as far as possible. But okay, so the proof uses something called the one-point compactification, which I will also just briefly explain. It's a topology course will give you this. But let's say, for example, the real line. It's not compact. Okay, here's 0. But then you can put a ball, a sphere, a circle with radius 1 on top of 0, and then it has you take this point up here, and then from this point to every point on the real line, you draw a straight line, and then you identify this point with this point. So this creates a map between the real line and all points on this sphere, except for this guy, like the North Pole. Okay, and this map is then continuous. You just use the usual topology on the circle as well. So, by just straightening it out and thinking of it as a line. So it's continuous back and forth, but now we have this additional point that we're going to call North Pole or infinity. Yeah. So then, if we add, so this circle here with that point is a representation of the one-point compactification, because now this set has the same topology as this guy, but this is compact, this one is not. And then you see that any open set around this ball will turn into everything outside a very big interval. Yeah, so the open sets around infinity is everything which is outside of a large closed interval or contains such. Well, the basis for the open sets around infinity is such intervals. Okay, so now if you think of a space like C0, these are functions that go to 0 as the variable goes to infinity. You can, so this we're going to call it R with a dash on top, so the 1-point compactification. So then C0 of R becomes the same as C of R dash with the restriction that f at infinity is equal to 0. So now, it's much easier to deal with continuous functions on a compact set. And then this is just, one-dimensional restriction, so to speak. So you get a hyperplane, if you wish. Now you have that this space is a subset of this with codimension 1, and that simplifies a bit. So in general, this is just like a visualization. In general, what you can do, you have your topological space X. And then you're just going to do union. And here I just write the symbol infinity. This is nothing but something I can do with my pen, right? Okay, now I added this point to it, which is called infinity. And then you need open or a basis of open sets around this guy to have complete the topology you already have in here to include this one. And then what you do is you just consider an open basis of open sets around these points will be everything which is, okay, so this is X bar, the completion, and then do X bar set minus any compact set. You define that as an open set of neighborhood of open sets around infinity. And yeah, that's how you do 1-point compactifications. And armed with that, he's able to prove this statement that if you have a topological space which has a countable basis, then it is metrizable. It has to be Hausdorff also. So compact Hausdorff. Wait, right. So that's the last proposition here. First, it says that a compact Hausdorff space is metrizable if and only if there's a countable base for its topology. And then it goes on to lift this to say that each locally compact Hausdorff space that has a countable base for its topology is metrizable. That's the end of 7.1. Yeah, I forgot which topologies that holds for. Doesn't matter. We have no, but if you have a metric, something that is, measures distance, that gives you topology, then many proofs become simpler. In particular, in RD, we do have a metric, right? Pythagoras theorem. So we're going to use that. So we're going to define a function f of x and y equal to the distance from the point x, y to, and here, of course, the distance to another point is just Pythagoras theorem. But also I can talk about distances to a set like E. And then I would do the infimum of the distance because so my x, y is out here, right? Or maybe inside E. And then I just take any point in here and compute the distance. And then I do the infimum, it will lead me to a point here, right? And it's theory to guarantee that there exists a point here. Well, that leads more to convex function theory. In convex, there exists a unique, this is a convex set which just happens to be, and it doesn't matter, I'm getting sidetracked. So the infimum exists, it gives the distance, that distance is 0 if and only if the point is inside the set, because it's closed. So this is a function which is non-zero everywhere outside of E and 0 inside of E. Now what we're going to do, we're going to divide it with the distance from x, y to the set f. Of course, once we're inside f, this is division by 0, which we're then going to interpret as infinity. So this is a function, it's 0 here,
and then rises, and by the time you hit the x-axis, you have infinity. So it's going to be much more steeper rise. But, I mean, because the problem is this corridor here, right? It gets more narrow and narrow all the time. So you need a very fast increase. And actually, that's not my f, because it doesn't satisfy that, right? Let's call him g, and then just do f equals to the minimum of 1 and g, right? So along some line here, this function g will become bigger than 1, and then we just chop it off and make it flat. So we, of course, then lose any kind of differentiability or nice properties that function g might have had, but we don't care. We just want continuity. So, yeah, this is our guy. So very easy to do in RD. Not easy at all to do in full generality of normal spaces or wherever now it holds. So read the topology course if you're interested in these kind of statements. Okay, now the second topic, partitions of unity. Is that it is the following addition. Partition of unity. Unity doesn't mean that you feel anything in common. Unity just means the number 1 here. So you start out with a compact set. Yeah, and then, okay, so here's your compact set K. Let's see if I can try to put an R2, and then we have some third axis here. And then just take the function, which is identically 1 on top of K, right? So outside of K, it doesn't exist. So this is unity. Now, let's say, so often in topological arguments, okay, let me look at K from on top. And to be simple, let's say now we have a covering of this by open sets. Yeah. So as long as every point X, you have a collection now. U, K, and K could be in any uncountable set, but again, probably topology course, equivalent definition, or even the definition of compactness in more abstract spaces is if you have a, no matter what sort of covering of open sets, a set is compact if and only if you can choose a finite subcovering. So you might as well start out with having finite to many of these sets. And in my picture, this is U1, this is my K. In my picture, I'm just gonna have 2 sets, right? So partition, we now wanna split up the function identically 1 in a manner which is consistent with our covering here, which means that we want functions for each open set. We want a function which has support inside of that open set, and let's sum up to this guy. So F1 dot Fn is a partition of unity with respect to K and this covering if support of Fk is a subset of UK, and these guys sum up to 1 for all x in K. I think we should also have the requirement that they're between 0 and 1. I'm pretty sure of that, but let me double check. Yeah, at least Wikipedia says that. But anyway, we can demand that sort of size. I'm definitely sure we don't want any negative. Right, we don't want negative numbers, so then we need this, because otherwise it sums up to 1. We would need to include negative numbers if one of them were bigger than 1. On papers. Okay, so what is this? I need a function here, which is identically 1. So let's say, you know, it's going to have a set where it's identically 1, and it needs to contain the piece of k, which is where there's no u2 helping us up. And then this guy needs to go to 0 before reaching the limit of u1. So it will be 1 inside here, and then you will have some sort of zone where it decays from 1 down to 0, and then it's going to be 0 everywhere outside. Of course, it exists also outside of the space. And then the difficult thing here, of course, the set where the other guy is identically 1 needs to be, it needs to follow this boundary here where this guy becomes 0, and then it just needs to encompass k. Then this guy is identically 1 here. And the difficulty is then, of course, to do this in a way so the zone where he decays is going to be the same. And you want to do this in a way such that these two functions here add up to become 1 in the overlapping zone on k. Here, when they split apart, doesn't matter. It just needs to be 1 on k. So proposition 2 says that we always can have a partition of unity. I do it in RD, the book does it for locally compact spaces. Slick proof. So for all x in K, pick Rx, some sort of radius, such that the ball with center x and radius 2Rx is a subset of UK for one of the possible case, right? So if I have a point here, x, since my U form a covering, it's at least inside one of the U's. If it's in multiple U's, doesn't matter, just pick one of them. And then, since this is an open set, I can always take a small ball around my x, which is inside of the open set, and the radius of that can be 2 times the number which I'm going to call Rx, right? So Rx is just half the radius of some ball you can fit in there. Now you use proposition 1. So the outside of your ball is a closed set, and the point x is also a closed set. So you have 2 closed sets. So you can find a function which is 1 on the point x and 0 outside of the ball. But actually, yeah, okay, so we need to shrink the ball a bit. That's why I have 2 Rx still. So instead we do use proposition 1 to find phi x, a function, such that phi x at x is equal to 1, and phi x is identically equal to 0 outside the ball with center x and radius Rx, so not 2Rx. Yeah, I just take a smaller ball here and force it to be 0 there. Then, since because the support contains the closure, And it could be that this bigger ball actually was tangent to the edge of U1. And if that was the case, then the closure of my phi would contain points outside of my U1 in the picture, UK in general, and that would have been bad. But by this trick of having two R here and just R next time, we avoid that, right? So the closure now, the support of phi Rx will be inside of this ball. Any ball with radius bigger than Rx. Okay, so now I have uncountably many points and uncountably many of these functions, but each phi x, the set of points where it's bigger than 0, strictly bigger than 0, that becomes a covering of my set K, right? So union over X in K for a set of points X, such that phi X of X. So, all right, so here I need another variable, phi X of Y is bigger than 0. So this is an open set, yeah, a continuity of the phi X's. Okay, so then I can pick a finite subcovering, which means I can pick out finitely many functions or points, x1 up to xn, corresponding functions, which have corresponding open sets here, such that the union of these sets cover my K. Now these are functions with values between 0 and 1. If I now look at this sum, we have a new variable j going from 1 up to n is the amount of functions. If I now sum them all up, I get a value bigger than 1, sorry, bigger than 0 for all points y in my compact set K. Otherwise, this wouldn't have been a covering. Good. So now I've managed to construct something extremely bumpy here, right? So if we're on the real line, this is my K, or I should paint it like a closed thing, then this thing can look completely whatever, right? But it's never 0. So it always turns around maybe like this. Here you can see maybe phi 1, phi 2, phi 3, phi 4, phi 5. Can imagine, or phi x1, phi x2. What do I do now with these guys? Well, I'm gonna introduce G1 equal to the sum among these functions phi xj, where xj is in U1. Okay? So just pick all the points that happen to land within the first guy, U1. All right, that's a subset of all of the points between 1 and n. Then G2, I'm going to do the same. It's just that now I don't want to pick the same point twice. So I do all the points in U2, which were not in U1. Okay, and then I continue like this. So G3. And so on, up till I get to Gn, right? Where I take the points which are in Un that has not been member of any of the previous U's. So now I have a function, now I have a set of functions which are 0 sometimes. Yeah, or G1 is going to be 0 outside of U1. Yeah, because the support of my phi xj, if xj is in U1, okay. I don't know that. So like when I did for every x, I picked an Rx such that it belonged to some UK. But this Rx, I mean, there could be multiple UKs here, and then the Rx that works for one may not work for the other. But there are finitely many of them. So let's say we have chosen the smallest one. Okay, then I know that if so, the smallest radius, so that this fits for all the UKs where this is true. Then when I come to this point, I would say, okay, this guy has support inside U1 because XJ is in U1. Saying this guy XJ here is in U2, maybe it's in U1 as well, but it doesn't matter. The support is inside of both U1 and U2. What I'm interested in is the support is like inside of U2 and so on. So these functions, this has support on U1, this one's U2, and so on. Still, they do not sum up to 1, but that Blackboard space that we deal with a very nice trick. So F K is going to set GK divided by the sum of all of the GJs. Now, if we sum up all the FKs, we get the sum of all the GKs. So we get this full sum divided by itself, we get the number becomes 1. Yeah, like the one from a partition of unity. The support of this guy is here. The only problem is that we can get 0 divided by 0 if we go outside of the opening covering. So that's why you can do a trick like this. Add here distance. Okay, so I need a variable here y, and then we just add distance from y to, let's say, k. All right. Then we are taking care of this problem with division by 0. That's it. That's your partition of unity in RD. So good luck reading the book of how to do the same in locally compact Hausdorff spaces. My lecture notes here says, section 7.1 is all about similar junk for locally compact Hausdorff spaces. Section 7.2, the first part concerns regularity of the measure. We do not need this part at all if we stick to just understanding the RD theory, because we know from 1.5 that all finite Borel measures are regular. But here's where we come to this. Remember, in the regularity, definition of regularity in more abstract spaces was that was a bit fishy, right? We had, let's just write whatever. Mu of u is equal to supremum mu of k, where k is a subset of u. This was supposed to be true for all open sets u, right? And then we had mu of a for any set a is equal to the infimum of mu of u, for now u for bigger guys, right? In RD, you could put a here as well. You don't need to worry about it being open, but apparently this is the point where this distinction is important. Exactly why, I can't really tell you. All right, here comes Orne again. Come in.
All right, so for the second time in a row, you're saved by Orne. But I think that was good. I would have just plowed ahead, and this is getting too long. So what I've done now is basically I've given you an overview look on what's going on in 7.1 and 7.2 up until the Riesz representation theorem starts. Of course, so that's 7.2.8. So I think this is very good. We cut it here, and you just try to go through that material before we move on with the actual proof of the Riesz representation theorems in the various forms of them. So also 7.3 has this dealing with sign versions, right? So 7.2 is just the non-negative version, version 1. Okay, and then the rest of the chapter, I'll probably give a very brief overview next time what that is, and then that's chapter 7. So hopefully next time won't be as long. Yeah, over and out.